Hello everyone, my name is Di Wen. I'm a staff software engineer in LinkedIn working on multimedia search. I'm presenting you the next section of our tutorial, video understanding. For video understanding, there are usually two parts of content we can utilize. The first part certainly is the visual frames. We can detect the concept of the video purely based on its visual frames and extract the visual feature embeddings from these visual frames. And the second part is a complementary part. That is, we can make use of the audio to classify different types of audio. Also, we can extract features as a audio feature embeddings, and then we can even convert the audio specifically to video transcript and to get a further enhance our video understanding part. Now let's go through different tasks of video understanding. The first task, the most fundamental one, is video classification. Video classification is for an input video, we need to classify it into a predefined specific topic. So we want to know what topic the video is about. And secondly, we want to not only about the topic of the video, we also want to know specifically what action inside the video, which we will need to leverage the temporal information of adjacent frames to understand a continuous actions inside a video. And lastly, we also want to segment out a coherent video clips for temporal topic localization. And the second task for video understanding is video segmentation in the spatial domain. For this task, we specifically are interested in segment out a video content, semantic video content inside the video frames with pixel-wise segmentation for every frame so that we can get an object-based video understanding of different content inside a video. And the last one is video captioning. This task, similar to image captioning, is to give a descriptive sentence for each inside input video as a basic caption description for the video. There are various challenges for video understanding. The first challenge is from model complexity, because we need to model both the spatial and temporal information in video understanding. That means the model and also the computation need extra complexity. Then the second challenge is the scale and efficiency. It means video data is usually much more denser than image data. And second, and the efficient training and online inference of a large video understanding model is usually very challenging. Let's talk about the video classification task in detail. In LinkedIn, we have general requirements for classifying each video with one or more labels. We also have specific requirements to classify a video into diverse sets of possible labels, which is related to different downstream applications. For example, to classify a topic of a video, and classify the actions of video, and classify and detect out the non-safe for work video and the low quality and spam video. So the good example for this would be a podcast video detection, investment video detection, or a running or exercise video detection. For action recognition, we usually model it as classification, but unlike a basic classification task, we need to leverage temporal information, which is key to capturing the actions. So a coherent video clips can range from a few seconds to minutes, which record a complete actions. This is an example for a action clips about throwing an axe. There are several public available datasets for video classification and action recognition. The first and probably the most famous one is the YouTube 8 million dataset. Initiated in 2016, the YouTube 8 million dataset has over 6 million video clips, with their length range from 120 seconds to 500 seconds. And they covered over 3,800 class labels. This is a graph for the distribution of the video clips across different labels in YouTube 8 million datasets. And later, in 2018, this dataset augmented itself to include action recognition data samples. The second famous dataset is the UCF-101 dataset, which was released in 2012 but specifically targeted on action recognitions. It provides over 13,000 video clips covering over 100 action classes specifically for action classification. So you can see an example for applying eye makeup action or baby crawling and serving, haircuts, etc. The third dataset is the HMDB dataset, which was released in 2011 also for action recognition, but with smaller volume. It has over 7,000 video clips covering 51 classes of actions. The fourth dataset, named the Kinetic dataset for action recognition, was released and updated by DeepMind from 2017. It has the version of 400, 600, and 700, corresponding to the number of action classes it contains. For the 400 dataset, it has over 300,000 video clips taken from YouTube. Each clip has over 10 seconds in the length. The fifth dataset, called the Spot 1 million dataset, was collected by Stanford University in the year of 2014. It is also extracted from YouTube video and contains 487 different class labels for video classification. It has the volume of over 1.1 billion video clips. This is another famous early large-scale dataset for video classification. Here comes the summarization of different video classification datasets in terms of their diversity and volume. You can clearly see that the YouTube 8 million dominates in both diversity as well as volume. And the second comes the Spot 1 million dataset, and then comes the UCF-101 dataset. After introduction to video datasets, let's come back to talk about another important task for video understanding. It is the temporal topic localization. For this task, we are not only to recognize the action label for a video, but also we want to segment out the specific timestamp for this action. So for this purpose, the YouTube 8 million dataset has released their third version to include a lot of label samples, including not only the action labels, but also the timestamps of the target actions. This is an example showing a blowing out candles examples inside this dataset. The next task for video understanding is video captioning. In this task, we are to generate a brief and concise textual description for an input video, describing its major steps. A good example for video captioning is for generating the step-by-step guidelines for the cooking recipe video. For example, you can see here, we can add some chopped basil leaves into it for this video, and then cut the top of a French loaf for that video. So in order to do this, a paper in 2019 has proposed a method which has been utilizing the video birds model to jointly modeling the probability of a input text and an input visual tokens. This model can be pre-trained and to maximize the propensity of the joint probability of text and video tokens. Then based on this pre-trained model, it can be used to apply to generate video captioning in the second step. Now it comes to the summary of video understanding tasks. We have introduced you several tasks range from classification, action recognition, to video captioning. And we have introduced you the unique modeling efforts required for video data process and the challenge of scale and efficiency, particular for video understanding. Now I'm presenting to you video understanding method using pre-extracted video embeddings. One of the major pre-extracted video features is the optical flow. You can imagine an optical flow as a dense displacement vector field for a given video frame based on its successive frames. Optical flow algorithms share a common assumption that the interframe visual changes are only caused by object movement. Therefore, it assumes that by displacing each pixel in the original frame with this vector field, you can totally cancel out the interframe visual changes. Since the optical flow is used to describe object movement across video frames under some assumptions, there are different ways to apply these assumptions. We start off with some definitions first. Let's say I, X, Y, T denotes the grayscale value of I at position XY at time t. And W is a displacement vector for a position XY. And the third entry of 1 indicates a fixed timestamp increase delta. Now, for grayscale value consistency, we want the points at time t to be exactly equal to the value at time t plus 1 at the position x plus u and y plus v. This is a strict constraint. And for gradient consistency, which is a weaker constraint that can better match the natural situations, we want only the relative difference between pixel values to be the same across t and t plus 1. So exact value don't need to be matched. For smoothness, we want neighboring pixels to have similar displacement vectors after calculation. The algorithm introduced by Brox in 2004 is an approximate solution to the optimization problem of optical flow given our previous assumptions. In this equation, you can see it's a sum over all spatial temporal points in a video. For each position x, we want to find a W displacement to roughly minimize this sum of three constraints. We can see the first term corresponds to the grayscale consistency, and the second term corresponds to the gradient consistency, and the third corresponds to the smoothness consistency. Here, psi is a monotonically increasing function, and alpha and gamma are hyperparameters. There are several important works on video classification using pre-extracted video embedding features. Here, we listed 3 important works before the deep learning emerged. And the first work is proposed by Ivan in 2008. It's called Histogram Descriptor of Space-Time Volumes. In this paper, the author proposed to use the XOG descriptor in the spatial domain and the HOF histogram of optical flow descriptor in the temporal domain, and then concatenate these two features and map that into a dictionary called Book of Features, which the author used these features for video classification. Another important work was proposed by Alexandra in the year 2008. In this paper, they extended the well-known HOG-based 2D descriptor to the 3D spatial temporal domain. By viewing the videos as spatial temporal 3D volumes, the author generalized the 2D HOG concept into 3D gradient and then pulled the histogram into a 3D HOG features, which they use applying to the problem of action recognition. The third important work we want to talk about is the stacked feature vectors, which we will further elaborate in the following slides. Feature vector is a well-known statistics characterizing a group of samples by their deviation from a predefined generative PDF function, usually a Gaussian mixture model. In Xiaojiang's paper in 2014, they proposed to use two feature vector layers to represent the input video. In the first layer is to match the feature vectors extracted from all the subvolumes inside a video into their feature vectors. And then they use a maximum margin technology to compress the feature vectors into a low-dimensional representation. This is the output of their first layer feature vector. Then the author used the first layer feature vector output as the input to their second layer. After learning a second GMM, they performed another feature vector layer with these preprocessed local feature vectors and aggregates them over the entire video. The output of the second feature vector layer is then normalized as the final video representation output, which is called stacked feature vectors.